So let's discuss this all-important cosmic microwave background radiation, and here we see the instrument associated with its discovery, and the gentleman as well, microwave receiver, and Arno Penzias and Robert Wilson standing in front of it, many years after they actually were making the discovery. Well, considerable amount of years before the discovery, calculations confirmed that if the universe began with a Big Bang, the remnants of that energy should act like a black body that fills all of space today. And the redshift from the expansion of space should convert the relatively energetic short photons to microwave, to radio, basically. Well, in the early 1960s, Robert Dickey and a team of colleagues from Princeton University understood this and began plans to detect it. And while they were making these plans, a few miles away, these guys working in Bell Labs, Penzias and Wilson, in 1965, had a strange signal in their horn antenna. And they were doing everything they could to understand the source of this unaccounted for noise. They were looking over their equipment real well. They were good radio engineers. They even had pigeons making nests in there and doing their dirty deeds in there and making a mess. And they would clean it up, took the pigeons out of there, and eventually had several iterations of that because the pigeons kept coming back. Eventually they got rid of the pigeons, and yet the noise was still there. And it was everywhere in the sky. It didn't come from just one particular location. No matter where they pointed this horn antenna, they noticed that same signal. Well, when they heard of the work of the Princeton team just a few miles away, they knew that they had discovered the cosmic microwave background radiation, which ultimately led to the Nobel Prize in Physics in 1978. Now, we've just recently discussed this phenomena, but just to review, after 380,000 years after the origination, the Big Bang itself, the electrons first were able to be bound to the nuclei. So prior to that, the nuclei were by themselves with the electrons, and the photons were bouncing around inside. And at 380,000 years, the electrons were bound and the photons could escape. So the universe becomes transparent. Well, observing this radiation is really viewing the universe as it appeared 380,000 years after the Big Bang itself, which is the oldest relic radiation that the universe produces. Interestingly, if you ever have the opportunity to look at the static noise on an old television set, the noise that you're looking at is, in fact, 1% background radiation. Microwave background radiation consists of about 1% of that noise. So that is looking at the oldest radiation ever produced. So the theory was that there should be a cosmic microwave background as a result of the decoupling that's currently seen to be about 3 Kelvin. It would originally, during the decoupling event, when the photons left the atoms, it would have emitted a orange 1000 nanometer 3000 Kelvin glow. But because there's been a redshift of a factor of 1100, in the here and now it would be a 1 millimeter peak wavelength, 2.7 Kelvin black body radiator. That's what it would appear to be, the entire universe from that radiation. Well, in 1990, COBE was launched, the Cosmic Microwave Background Explorer, actually the Cosmic Background Explorer, and the results of this mission were nothing short of astounding. What you see here is a graph. The line is a plot of a perfect black body radiator, theoretically, at a temperature of 2.725 Kelvin, plus or minus 0.002. The data itself is the dots you see here. Now, this is essentially unprecedented in astronomy and cosmology. You don't ever expect to see data that matches a theoretical model so perfectly. When you do, it really makes you sit up and pay attention. In this case, what it revealed is that because of this almost perfect theoretical fit that it really rules out any other source other than a hot Big Bang beginning to the universe. So because of this, it made headlines all over the country, at least. I remember this event and seeing headlines that said things like, "The Holy Grail of Cosmology has been discovered." Namely, the evidence for a hot Big Bang beginning to the universe is irrefutable, essentially, because there is no other circumstance that could produce such a phenomena. So you can see why that's so important. This is a map that Kobe produced, and what you really see here is temperature variations, very small temperature variations, deviations from the perfection of the Planck curve that's shown here. They don't really hardly show up in the data unless you look at it with greater precision. Well, since the origin of the universe is such an important thing to nail down, the next generation of detectors is in the form of what's called WMAP, the Wilkinson Microwave Anisotropy Probe, and it actually turns out to be placed at the L2 position, Lagrange position. The contribution that it provided is that it's a much better instrument, higher resolution of the black body radiation, 45 times the sensitivity, 33 times the resolution. And the data from this produced information about the age, geometry of the universe, the constituents of the universe, aspects of the evolution. What you see here is the Kobe results that we just discussed, and here is a much higher resolution of the WMAP, kind of like 240p versus maybe 1080p, high definition. Well, from this, the results from this data is that the cosmic microwave background radiation temperature is nailed down to a perfect black body, almost perfect black body radiator of 2.725 plus or minus 0.0002 Kelvin. The very small temperature fluctuations provide evidence for seeds of galaxy formation. It gives us knowledge of the temperature in the past, which is consistent with the theoretical determination of 25% helium in the early universe, produced in the early universe, also consistent with what we actually see. And the age of the universe comes out at 13.73 plus or minus 0.012 billion years, gigayears. So this has been a phenomenally important mission, and even now in 2012, there is another, even more advanced mission called the Planck Surveyor that's doing the same thing at even higher resolution, and more information is going to come out of that. This has probably been the most important mission in terms of informing us about the cosmology of the universe, of anything that's preceded it. Something that's not that well understood, but is certainly important in our understanding of the development of the universe, is where the galaxies came from. But the cosmic microwave background radiation has secrets to the seeds of galaxy formation. Quantum fluctuations, which is synonymous with virtual particle production, during that inflationary period we were talking about, were stretched to macro size during inflation. And those fluctuations, kind of like little explosions, firecrackers going off, produce sound waves propagating through the gas of the early universe, which is also associated with, then, those sound waves, pressure, density, and temperature variations, all go hand in hand, traveling through the expanding universe. And they're moving really fast, but they cease after 380,000 years. So they're traveling for 380,000 years, and then at recombination, or at that decoupling event, they stop. And so they're imprinted in the background radiation. Now, sound waves consist of compression and expansion regions, and that sound wave then leaves its imprint in the background radiation as higher and lower temperature regions. Those higher and lower temperature regions are what we see in the WMAP data we just looked at, as variations in temperature of about 1 part in 100,000. So we have a black body radiation profile of 2.73 Kelvin plus or minus 0.00003 Kelvin, or plus or minus 300 microkelvins is shown here, from warmer in the red to cooler in the blue in this case. So these tiny temperature variations reveal that there are density variations. As I said, they go hand in hand. So these density variations are associated with higher regions of gravitational instability and therefore seeds of galaxy supercluster formation. Now, after 13.7 billion years, we're observing this background radiation. The size of these variations is about 1.2 degrees. Well, that's where they cluster. This graph here is showing basically abundance level here versus angular size of the spread of the variations in the background. The peak of the spread occurs at about 1.2 degrees. So 1.2 degrees seems to be the most frequent variation size in angular extent. And it also corresponds in actual extent to about 1 billion light years. Now this is consistent with what we see in the superclusters that are permeating the universe. In addition to that, in these there's overtones in the sound waves, like different modes of vibration on a string. And that's what this data out here is. And it's a little more complex to ferret this out. But what the overtones reveal is that there is more dark matter in the universe over regular matter, about 5 times as much, in order to produce the kind of overtone profile that is seen here. So this is wonderful data to inform us about where the galaxies come from. And in upcoming years, the Planck surveyor will inform us even more precisely about exactly what's going on in this and other cosmic parameters as well. So the next major era in cosmic history is known as the Dark Ages. After recombination, the universe just expanded and cooled for about 400 million years. The photons were stretched over this time to the infrared, and we just have a very quiet, dark, extended expansion. And during this time, there's no light emission, except for the 21 centimeter radio emission from hydrogen, which of course cannot be seen, although obviously proper detectors could see that, and actually it's being searched for. So this is a very uneventful time, ending in the very first stars that we haven't even discussed yet. We've discussed population 1 and 2, but this is population 3 stars, the very first ones where cool regions of gas began to collapse under their own gravity as a result of what we just discussed, the seeds of galaxy formation, temperature variations in the background radiation. So we have those seeds and certain regions of the gas combining together, forming really huge stars, unprecedentedly huge. They are metal poor because no metals have been really produced yet. So they can produce excessively massive, luminous, and short-lived, just a few million years. 100 solar masses to about 250 solar masses. In just a few million years produce huge supernova and black holes. And the very largest, up to 500 solar masses, they produce black holes without ever producing supernova. So these are very high luminosity stars, therefore producing ultraviolet photons, which reionizes the surrounding gas. Now I say reionizes because, remember, before 380,000 years, everything was ionized. It was ionized hydrogen. And at 380,000 years, you produced atoms. So these atoms have existed from 380,000 years now to 400 million years. And now, for the first time in all that extended length of time, we have gas being ionized once again. So it's lit up. So we see lit up regions. This is an artist's conception. We haven't been able to image this. Nevertheless, it must have been quite a sight. And this marks the beginning of the age of stars and galaxies, because now stars are forming. And so the era of the galaxies we have protogalactic clouds forming, population 2 stars, and normal galaxies, from the protogalactic clouds, starting at about 600 million years, maybe just a little bit before a billion years. And the era of quasars extends from about just under a billion to 3 billion years, as galaxy interactions were frequent, producing supermassive black holes, which we know are associated with active galactic nuclei, namely quasars. And there's even evidence for the galaxies forming clusters within about 2 billion years. So that brings us up to the era of the galaxies, which is real close to the current time. And how the galaxies formed, let's just consider now for a moment. So early galaxy formation can be characterized in brief. We have a theme being the rate at which stars are formed. And as we study the early galaxies, ellipticals seem to develop their stars in just a frenzy that takes place in about a billion years, and then it's over. So here we see elliptical galaxies. After about a billion years, the star formation has essentially gone to zero. And as a result of that, they lose their massive stars real quickly. Any OB stars they would have had would be burned out, and they aren't replenished. So the galaxy becomes redder and dimmer. Whereas spiral galaxies, see this curve, they never produce stars that quickly. It trails off, but over about a 10 billion year period, which has been the period of time that the spirals have been producing stars. Decreasing in rate, but slow enough, and the conditions are right so they can continue to produce stars. Basically because the spirals have plenty of gas to produce new O and B stars, as we've already discussed earlier. So the stellar formation rate seems to determine the initial structure of the galaxy. So this is very sketchy, so it'll only take about a minute or less to describe it. We have spiral galaxy formation here. We start with a cloud. If the stars form slowly within it, there's time for the gas to settle out gravitationally into a disk, producing a spiral. And the star formation can continue in the disk since there is enough gas to produce ongoing star formation, which then perpetuates itself. On the other hand, for elliptical galaxies, if the stars form quickly, for various considerations, density and rotation rates and whatnot, that could inform that, the pregalactic gas is really used up in star formation very quickly, so a disk doesn't form, and it just forms essentially a ball of stars. So there's a difference between spiral and elliptical. Of course, as we have investigated, collisions and mergers really can radically change the evolution and future of a galaxy. So this is just a brief synopsis of the two major galaxy types. So this brings us to today, 13.7 billion years from the Big Bang beginning, with a current temperature of 2.7 Kelvin. Now, several generations of stars have come and gone in the Milky Way galaxy, taking about 8 billion years or so to produce the conditions in this certain part of the Milky Way galaxy to enable a metal-rich star to produce a metal-rich planet like Earth, rocky planet like Earth. And it can only form in a very special time and special place in the galaxy. So chemistry has emerged from the elements associated with this planet, linking atoms to form molecules. The DNA genetic code mysteriously emerges, no one knows how, but life develops on Earth. And in all of its incredibly complex manifestations, and sentient, self-aware humans emerge and try and make sense of it all. The classic ape to human scene there, which is not even scientifically correct. And the thinker at the end, who's starting to stoop back down again, but thinking so hard he's discovering the elliptical nature of the orbits in the cosmos. I'm just going to extend this video a little bit to highlight a couple ways in which inflation helps us with some problems with the Big Bang. Well, so we know the Big Bang is strongly supported by the evidence of the cosmic microwave background radiation and other things like light element abundances, the production of helium in the universe, which we haven't really delved into too much. Well, the grand unified theories of the Big Bang model, they're not proven, but they do suggest the inflationary period, as we went through. It's a wonderful match to what we observe, and it also answers some problems or concerns that we have, especially without it. One being, where does the structure come from? Okay, the CNBR shows these temperature variations, showing that they were there early on, but what initiated them? Also, why is large-scale structure so uniform? The cosmic microwave background temperature is within like 1/100% or less of other regions. It's known as the horizon problem. Now, these are a little bit related. So, just to review then, the structure problem, we have at very small quantum scales, we have energy fields, quantum fluctuations, particle production pairs producing quantum ripples in the fabric of space-time, and they can be the seeds of density enhancements that would grow into galaxies, but they're just too darn small. They're quantum fluctuations, and we need something the size of galaxies. Well, the inflation would have expanded those ripples from the size of maybe a nucleus to the size of a soccer ball, or even the solar system, depending on what model is being used, in about 10 to the negative 35 seconds, which can then explain the current structure. So this region of space-time would be rapidly expanded so that the quantum-sized structures would stretch out into macro-sized ripples. Now, the second issue, the horizon problem, as it's called, is associated with what we call the cosmic light horizon, which really refers to the farthest distance that we can see from Earth. So here we are at Earth, and photons are coming in from every direction, but the farthest we can see would be light that has traveled the entire time that the universe has been around to emit those photons, which we know actually was 380,000 years after the Big Bang, which is almost right to the beginning. But this defines what we refer to as our cosmic light horizon. And that's our present horizon. It's from a region in time, 13.7 approximately billion years ago, limits how far we can see photons. In other words, if there's light coming from further away, there hasn't been enough time for the light to arrive at our location on Earth so we can see it. Now, as time goes on, space expands, so these photons are stretched, which is very well clarified in this image here. And all this is consistent with data that we've looked at, images that we've taken to show the nature of light from far reaches in the universe. But this cosmic light horizon is not a limitation on the size of the universe as it is a limitation on the time light has had to travel that we can see. So theoretically, there's no possible way that we can see anything beyond this horizon because of the limit of the age of the universe. So the horizon problem, as it's known, comes from the consideration of the uniformity of the temperatures and densities everywhere we look in the universe. And here's how the problem goes. If you look at the universe in one direction and look as far back as you can, deep into the cosmos as possible, you're looking at what the universe looked like 380,000 years after the Big Bang. So that's almost 14 billion years ago. A little less than 13.7, or right around there. And now you turn around and observe the universe in exactly the opposite direction. What you notice is that it looks essentially the same. The temperatures are the same, densities are the same, as revealed by the cosmic background radiation, in fact. You're going to see what it looked like in the other direction 380,000 years after the Big Bang. So this almost exact identical picture you get doesn't really make sense. And the reason why is because there's just too vast of a expanse between those regions of space for them to have communicated in the 13.7 billion years they've had to communicate. You're now looking at a distance, from our point of view, of over 27 billion light years. And that's just too far for information to have communicated from one end to the other. So that's the problem. It can be thought of like this. Take a stove and set it at 350 degrees and let it come to temperature. Put a thermometer in the stove. You'll notice 350 degrees no matter where you put the thermometer in that stove. Now open the stove, put a thermometer a foot away and another one on the other side of the room. Wait a couple minutes. You'll notice that the thermometers will not read the same thing because the molecules have not had enough time in the room and the oven to thermally equalize. They haven't had time to properly mix. So they haven't communicated their collective answer to the temperature of the room. Say to an outside observer, what's the temperature in the room? Well, we can't really say. It varies. So that's the problem. How did they come to have the same temperature and density? Well, inflation answers this question. So here's a graph of time and distance, and we have the two regions of space, A and B, at the very beginning, very close to each other before inflation. The two locations had no contact since inflation, but they were in contact prior to inflation. So for instance, at 10 to the negative 38 seconds, the light particles had plenty of time to thermally equalize in temperature and density. And then they enter inflation, 10 to the minus 36 to minus 10 to the 32, where they're pushed apart at hyper velocities, hyperinflated, so that they're far out of contact with each other. It's all over in a trillionth of a second. So you have these two regions here now that have been in thermal contact. So they go ahead and reveal themselves, their characteristics, over the next 13.7 billion years from opposite directions, so that us Earthlings can see that long ago there was a point in time where they had communicated with each other. Now there's no violation of the speed of light here because space can expand at any arbitrary rate. So putting all this together, we come to the conclusion that a inflationary hot Big Bang model of the universe is by far the best model that we have to explain the universe we live in.